Welcome back. Today we are going to talk about another method to model turbulence, large eddy simulations. There are largely three classification of methods using which you can model turbulence. First one is DNS, which is called direct numerical simulation. In this particular method, you do not model turbulence at all. You actually resolve all the scales in space and all the scales in time as well. And these scales are called Kolmogorov scales. And in the upcoming lectures, we will discuss that how we can estimate these scales for a particular flow. And if you resolve all these, you will be able to resolve the turbulence in its entirety. But these are very expensive. So for high Reynolds number, as written here, it is prohibitively expensive. That means the solver becomes very stiff, the time steps becomes very small, and the resolution that is required at each and every point in the space also very small. Therefore, the overall simulation becomes very heavy, and usually this kind of simulation is not preferred unless you want to do something very simple like a flow past a circular cylinder. These are not done. Then comes RANS, which we have discussed in our previous lecture, and these lectures are present in our YouTube channel. You can go back and watch them. In Reynolds averaged numerical simulations, you resolve only the mean flow. This particular mean flow is filtered with the help of Reynolds averaging. In this method, the flow variable phi is integrated over time, and there is some criteria that you have to follow to get the time for which you want to perform the integration, and this time scale comes from the Reynolds number of the flow and the turbulence property of the flow. This particular flow misses the unsteady turbulence, and if you are using a viscosity based model, then that kind of model are also isotropic. That means you won't be able to cover turbulence which are anisotropic. Then the third one is the large eddy simulations, and this is what is the main topic of this particular lecture. In large eddy simulations, as the name suggested, we resolve all the large eddies. So in easy language, you can understand eddies by these circular motions, and if these are the grids, let's say you have this circular motion about this particular solid body, there is this circular motion. If you want to resolve this, you can create your grid something like this, and you will be able to resolve this. But if there is a smaller eddy, something like this here, these you won't be able to resolve. You have to choose what you want to resolve and what you don't want to resolve, and you can choose that by setting your grid spacing, or you can call this delta, which is the filtering scale. And if you filter to a very high resolution, then you will be able to resolve more and more eddies. That means more and more accuracy. There is a control, but as delta tends to very small value, then you will be doing this direct numerical simulation. This particular model, this does not work very well for wall bounded flows. Near wall, there are methods which is a blending between this Reynolds averaged method and the large eddy simulations, which also we are going to discuss in this particular series. First of all, in order to find out that what particular resolution that I require such that I will be able to perform this large eddy simulations, this number of cell requirement for Reynolds averaged simulations is very less, because it only resolves the mean flow compared to this even in free space. So away from this also the requirement of cells are high for large eddy simulations. Therefore, the overall expense of the computation is in the order of first lowest is RANS, then LES, then DNS. So first what we are going to do now is, first we will do a RANS simulation, which is k omega SST we are going to use this k omega SST model to perform a flow past a square cylinder that we have taken for almost all our lectures. This is our model problem. Square cylinder is comparatively harder to solve compared to a circular cylinder, so that's why we are choosing this. See you in the next lecture. Thanks for watching, and if you like the content of our channel, then please like, comment, share and subscribe.